169 years have passed since the last major rupture on the southern San Andreas, and a peer-reviewed model now puts the stress stored in that fault system at or above its highest level in 1,000 years. This week, a second research team said the fault is also sliding faster than anyone thought, across a 10,000-year record. Here is what that combination actually means. What the headlines got wrong about it, and why a small earthquake nobody catalogued on Friday tells you more about your warning time than either study does. The San Andreas Fault is moving faster than anyone thought. That is the sentence that ran across American news outlets this week, and it came out of a county park in the Santa Cruz Mountains where the fault runs directly underneath the picnic tables. Researchers from San José State University, led by geology professor Kim Bliznyuk, went into Sanborn County Park in Saratoga, sampled the rock, and came back with a measurement of how fast that section of the fault has been sliding, not over the last century, not over the last 1,000 years, but over the last 10,000. What they found is that the rate did not slow down. Across the entire window, the fault kept moving at roughly the same speed. And the speed in the Santa Cruz Mountains turned out to be comparable to the speed measured far to the north along the coast, which contradicts the working assumption that the fault gets progressively lazier as it runs south toward the Bay Area. Here's the first thing you need to know before anything else, because almost every headline this week skipped it. The research is unpublished. It has not been peer-reviewed. No number, in millimeters per year, has been released to the public. Every outlet that covered it said so, usually in the 4th or 5th paragraph, and almost nobody who shared the story got that far. So when you see a post telling you the San Andreas is now slipping at some specific alarming rate, that number is invented. It does not exist yet. What does exist is the shape of the finding, and the shape is what matters. Bliznyuk described it this way to ABC7. The rate appears to not decrease along the San Andreas Fault, but it appears to be constant over this 10,000-year window that we were able to document. That is a quiet sentence about a very large object. The San Andreas runs roughly 800 miles, from the Salton Sea in the southern desert, northwest past San Bernardino, past Los Angeles, up through the Carrizo Plain, through Parkfield, through the Santa Cruz Mountains, out to sea just south of San Francisco, and back onto land along the north coast. It is the boundary between two tectonic plates. It is not a crack in the ground. It is the seam where 1/3 of a continent slides past the Pacific Ocean floor, and it has been doing that for about 30 million years. So when a research team tells you the seam is moving faster than the textbook said, the correct response is not panic. It is a question. Faster than what? Measured how? And what changes because of it? The method here is worth understanding because it is the reason this result reaches back 10,000 years instead of 1,000. It is called cosmogenic nuclide dating. Cosmic rays are constantly striking the surface of the Earth. When they hit quartz, they produce a rare isotope called beryllium-10 inside the rock. The longer a rock surface has been sitting there exposed to the sky, the more beryllium-10 accumulates inside it. Measure the concentration, and you can calculate how long that surface has been exposed. It is a clock built into the stone. Now pair that clock with geometry. A fault does not just move, it carries things with it. A stream channel that once ran straight across the fault gets cut in half, and the two halves drift apart. A ridge gets offset. A terrace gets displaced. If you can date the landform and measure how far it has been shifted, you have a slip rate. Displacement divided by time. That is the entire calculation. Distance over duration. Prior work on the Santa Cruz Mountains section leaned on landforms that reached back roughly 1,000 years. Bliznyk's team found and dated features that reach back roughly 10,000. That is a 10-fold increase in the length of the record, and it changes what the number means. A rate measured over 1,000 years can be an accident of which earthquakes happen to fall inside your window. A rate measured over 10,000 years averages across many complete earthquake cycles, which makes it a much better description of what the plates are actually doing. And the answer, across all 10 millennia, was that the rate held steady. Bliznyk also made the point that the Santa Cruz Mountains rate resembles the rate measured on the North Coast section. That sounds technical. It is not. The assumption being challenged is that the San Andreas sheds motion as it runs south, that some of the plate movement peels off onto other faults, so the main strand slows down. If that assumption is wrong on this stretch, then the section of the fault, sitting directly underneath one of the most densely built regions in the United States, has been quietly banking more motion than the models credited it with. For context, and only as context, published slip rates along the San Andreas run roughly 20 to 25 millimeters per year on the north coast, and higher, in the mid-30s, along the central Carrizo section. Those are existing literature values. They are not Bliznyk's result. Nobody outside her team has her result yet. Every headline this week led with the word faster. The scientifically interesting word is constant, and here is why. Earthquake recurrence on a locked fault is, at its simplest, an accounting problem. The plates move at a long-term rate that does not care what the fault is doing. The fault surface itself is stuck, held in place by friction. The difference between how far the plates have moved and how far the fault has actually slipped accumulates as elastic strain in the rock on both sides. It builds like tension in a bent branch. When the accumulated shortfall reaches the amount the fault can release in one go, it releases it. That release is the earthquake, which means recurrence interval, roughly, equals characteristic slip divided by slip rate. Slip rate is the denominator. Raise the denominator, and the interval shrinks. A segment that was thought to need 200 years to reload might need considerably less than that. Nothing about the fault changed. The number underneath the division sign was wrong. That is the practical meaning of faster. It does not mean the fault is accelerating. It does not mean something new is happening down there. It means our arithmetic about how often that stretch of fault produces earthquakes may have been too generous, and the correction runs in the direction nobody wants. Now take the other word. If the loading rate is constant across 10,000 years, then the process feeding energy into the fault is regular, steady, predictable in the loading sense. But the paleoseismic record shows that the release is anything but regular. Earthquakes on the San Andreas cluster and then go quiet for centuries, with intervals that vary wildly. Put those two facts together, and you get an uncomfortable conclusion. If the input is smooth and the output is jagged, then all the irregularity lives in the fault itself, in its strength, in its geometry, in how well it healed after the last rupture, in the pressure of fluids inside the rock. The unpredictability is not in the plate motion, which we can measure very well from space. It has been pushed entirely onto the fault, which is the part we can observe least well, buried kilometers underground. The research made the plate motion more knowable and the earthquake less knowable at the same time. And that brings us to the study that landed 10 weeks earlier, which almost nobody connected to this one. In the middle of June this year, a different team published a very different kind of work in the Journal of Geophysical Research, Solid Earth. Lead author Lillian Burkhardt, a research affiliate at the Hawaii Institute of Geophysics and Planetology, and a scientist at the University of Bern, looked at the other end of the fault system, the southern San Andreas and the San Jacinto Fault that runs broadly parallel to it through Southern California. This study was peer-reviewed. That distinction matters, and it will keep mattering through the rest of this video. The team built a 1,000-year record of earthquakes on those two fault systems, and the way they built it is remarkable. Part of it came from radiocarbon dating of sediments that had been displaced by past ruptures. The other part came from trees. When a large earthquake hits, it tilts trees, uproots them, and disturbs the drainage that feeds their roots. A tree under that kind of stress lays down a narrow growth ring, and tree rings can be dated to the exact year. Burkhardt described it this way. By precisely dating these anomalies, which acts as a natural calendar going back centuries, scientists can identify years in which a major seismic event likely occurred in the region. They fed the 1,000-year history into a physics-based model of how stress accumulates and transfers between the two faults. And the model returned a result that got far less attention in June than it deserved. Stress on multiple segments of the southern San Andreas and San Jacinto systems now sits at or above the highest values of the past 1,000 years. Read that again. Not the highest in living memory, not the highest since instruments were installed. More stress stored in those fault segments than at any point since roughly the 11th century. Burkhardt's own summary? Right now, with stress at historically high levels across the region, and more than 160 years elapsed since the last major rupture, the system is in a critically loaded state. The last major rupture on the southern San Andreas was the Fort Tajan earthquake of 1857. That was 169 years ago. The northern San Andreas last ruptured in 1906, 120 years ago. The Hayward Fault, which runs under the East Bay, last let go in 1868, 158 years ago. Every one of those clocks is running long by the standards of its own history. And what makes the pairing with the Santa Cruz Mountains work meaningful is that the two studies do not depend on each other at all. One is a field measurement using isotopes in rock. The other is a computer model built from sediments and tree rings. Different halves of the fault, different methods, different confidence levels. They arrived at the same edge of the same conclusion from opposite directions. The loading term is bigger than the textbook assumed. That independence cuts both ways, though. The weaker result does not get to borrow credibility from the stronger one just because they agree. One of these has cleared peer review. One has not. Keep them separate in your head. The Burkhardt study produced a second finding that is arguably more alarming than the stress number, and it concerns a place most Southern Californians drive through without a thought. Cajon Pass is the gap between the San Gabriel Mountains and the San Bernardino Mountains, the corridor that carries Interstate 15 and the main rail line from the Mojave Desert down into the Los Angeles Basin. It is also where the southern San Andreas and the San Jacinto Fault come close to each other, not touching. That is the entire point. At the surface, the two faults do not intersect at Cajon Pass. They meet far below it. And that geometry, according to the model, makes the pass behave like a gate. In Burkhardt's words, we also found that Cajon Pass may act as an earthquake gate, sometimes blocking large ruptures from crossing between the faults, and sometimes allowing them to pass through and involve both systems in a single event. Think about what that means mechanically. A rupture starts somewhere on one of these faults and begins tearing along it at a couple of kilometers per second. It reaches the junction. And at that moment, one of two things happens. Either conditions at the intersection allow the rupture to jump onto the neighboring fault and keep going, or they do not, and the rupture stops there. Burkhardt put the condition plainly. A rupture crossing from one region to the other requires favorable conditions at depth. If the rupture is running shallow when it arrives, the gate stays shut. The model's finding is that whether the gate opens depends partly on whether both systems are similarly stressed when the rupture arrives, which, according to that same model, they now are. A through-going rupture involving both fault systems is not a slightly bigger version of a single fault earthquake. It is a different event, longer rupture length, longer duration of strong shaking, and a footprint that covers San Bernardino, Riverside, the Inland Empire, and the eastern Los Angeles Basin at the same time instead of one after another. Roughly 20 million people live along those two fault systems. The study named Los Angeles, San Bernardino, Riverside, and the Coachella Valley as significantly affected in that scenario. The baseline number the researchers carried alongside all of this is the United States Geological Survey estimate that there is a 75% chance of a magnitude 7 earthquake somewhere in California in the next 30 years. That number has been on the books for years. Nothing this week changed it. Now the correction, because this is where most coverage goes wrong and where you deserve a straight answer. A critically loaded fault is not a fault with a timer on it. The Burkhardt model says the southern system holds more stored strain than at any time in 1,000 years. It does not say the fault will fail when strain reaches some threshold, because faults do not have a fixed breaking point. Whether a fault ruptures depends on the stress state, on the pressure of fluids in the rock pores, on the local geometry of the fault surface, and on how thoroughly that surface has healed and relocked since the last time it moved. A fault can sit in a critically loaded state for decades, or for centuries. What high stored strain does change is the size distribution of what is possible. The more strain is banked, the further a rupture can run once it starts. The more likely it becomes that the rupture will jump a structural barrier instead of stopping at it. It shifts the odds toward the larger end of the range. It does not schedule anything. And if you want the definitive lesson in why not to treat any of this as a countdown, it is written into the fault itself at Parkfield. Parkfield produced magnitude 6 earthquakes in 1857, 1881, 1901, 1922, 1934, and 1966. Average interval, about 22 years. That regularity looked like a gift. So the Geological Survey did something no agency had done before, or has done since. It issued a formal public dated earthquake prediction. The next Parkfield earthquake would occur before 1993. They wired that stretch of fault with more instruments than any patch of ground on Earth and waited. The earthquake arrived on September 28, 2004, more than a decade late. And when it came, it ruptured in the opposite direction from every previous event in the sequence and produced ground motions considerably stronger than the models had predicted. The best instrumented fault on the planet, with the cleanest repeating pattern in the catalog, made the most confident prediction in the history of American seismology look foolish. Any conversation about slip rates and recurrence intervals that leaves Parkfield out is selling you something. And as it happens, Parkfield is exactly where the next part of this story takes place. While the San Andreas headlines were circulating on Friday, something small and strange happened on the fault itself, and it went into no public record at all. At approximately 11:37 in the morning Pacific time, a clear arrival appeared on the seismograph waveform for the Parkfield section. Broad, well-defined, localized, distinguishable by eye from the ordinary microquake noise that station produces all day. It did not show up on the Petrolia station up north, and it did not show up in Nevada, which means it was local rather than a distant event registering everywhere. By eye, it looked like something in the range of magnitude 2 to 2.5. 15 minutes later, nothing had been published. As of yesterday, still nothing. There's no catalog entry for that time. Here's the full public record for the Parkfield corridor across 38 hours. A magnitude 0.62 near Cholem. A magnitude 2.08, 22 kilometers northwest of Parkfield. A magnitude 1.5 near New Idria. 3 events. And between the first 2 of them, there is a gap of 8 hours and 44 minutes with nothing in it. A gap that swallows the arrival on that waveform. The nearest catalogued event came 1 hour and 14 minutes later, 22 kilometers away, and it is still flagged automatic. No human analyst has reviewed it. This is not a cover-up. It is the detection floor. And it is the single most useful thing in this entire story. The earthquake catalog is not a curated narrative written by someone deciding what the public should know. It is an automated pipeline. Software watches the incoming waveforms, associates arrivals across multiple stations, and locates an event when enough stations agree. Every network has a magnitude of completeness, a threshold below which events simply are not reliably detected and located. Around Parkfield, the station coverage is excellent and that threshold is low. But a small event that arrives when the automatic associator is struggling, or that registers well on one station and poorly on its neighbors, does not get located. It falls through. And notice how anyone was able to spot the discrepancy in the first place. The raw waveform data is streamed publicly in real time, which is precisely why a gap between what the ground did and what the catalog holds is visible at all. Secrecy would require hiding the waveforms. The waveforms are the thing that exposed it. The same weekend produced a second lesson in the gap between what happened and what got reported, and this one is easier to check. In the 24 hours of Friday, the entire state of California logged exactly 3 catalogued earthquakes of magnitude 2.5 or greater. 2 of them were at Coso Junction in the volcanic field north of Ridgecrest. One was near Ferndale on the far north coast. That is the whole list. The state that 2 studies had just described as critically loaded produced 3 earthquakes above magnitude 2.5 in a full day. At Coso, though, there was a swarm running. A query of the catalog across the Coso, Little Lake, and Ridgecrest area for that same period returns 58 events. The sequence opened with a magnitude 0.61 and climbed over the following 17 hours to a magnitude 3.29 at 26 minutes past 10 in the morning. That escalation is the tell. Aftershock sequences start with their largest event and decay. This one ran the other way, which is the signature of a swarm. The depths are the other unusual feature. The whole cluster sits between roughly 2.5 and 4.5 kilometers down, packed tightly around 2.5 to 3. That is remarkably shallow for California outside a geothermal or volcanic setting, and Coso is both. The California Volcano Observatory reports no ground deformation and no indication of magma moving toward the surface. The alert level is normal, the aviation code is green, but Coso is also an active geothermal field, generating somewhere around 250 to 270 megawatts, drawing heat from an intrusion about 5 kilometers down, with fluid being reinjected into the ground continuously. A Navy-operated array has cataloged roughly 294,000 events there since the mid-1990s, and published work using that catalog found a strong correlation between short-term jumps in the seismicity rate and seasonal changes in the volume and temperature of reinjected fluid. A shallow swarm in an active injection field is, at minimum, a candidate for something partly human-caused. Now, the reporting. A syndicated national story on Friday said 7 tremors had been detected near Coso Junction, with the strongest at magnitude 3.4. The reviewed catalog holds far more than 7 events, and the reviewed magnitude of that largest event is 3.29, published as 3.3, not 3.4. Both figures were provisional automatic values that a wire service picked up early and never went back to correct. All of this landed in the middle of a month that felt, to a lot of people online, like the planet was coming apart. And that feeling produced the claim this video has to address directly. In the 30 days ending yesterday, the world recorded 12 earthquakes of magnitude 6 or greater, a magnitude 7.7 in Indonesia on the 14th, a magnitude 7.4 in Colombia on the 10th, a magnitude 6.7 beneath southern Peru on the 20th, a magnitude 6.9 in Indonesia on the 15th, a magnitude 6.2 in the Scotia Sea yesterday morning. A post pairing that sequence with a caption written in the voice of the San Andreas Fault itself. 4 words. "It's my time to shine," went around the internet this week, and an enormous number of people found it plausible enough to share. So let us take it seriously enough to answer properly. 12 magnitude 6 plus earthquakes in 30 days is not a surge. The long-term global average is roughly 130 to 150 per year, which works out to about 11 or 12 per month. This month is ordinary. It only looks extraordinary because 3 of those events landed near populated areas in the same fortnight, And even if there had been a genuine global spike, the mechanical connection people are imagining does not exist. There are two ways one earthquake can influence another. Static stress transfer is the permanent change in stress caused by a fault slipping, and it falls off extremely steeply with distance, roughly as the inverse cube. At 10,000 kilometers, it is not small. It is unmeasurable. Dynamic triggering, where the seismic waves themselves nudge a distant fault as they pass, is real and documented. But it acts only during the few minutes the waves are traveling through, and the stress changes involved are on the order of kilopascals. The stress that plate motion loads onto the San Andreas over a single year is on the order of megapascals. That is a factor of 1,000. The plate boundary loads the plate boundary. Indonesia does not load California. The three named earthquakes occurred on three different plate boundaries with three different mechanisms, two of them at intermediate depth inside a sinking slab of oceanic crust. They have nothing to do with a transform fault in California, and the San Andreas has been loading at the same steady rate through all of them, which is, after all, exactly what this week's research says it has been doing for 10,000 years. So where does that leave you practically this morning? The first thing to watch for is publication. Bliznyuk's slip rate work has to clear peer review and appear in a journal with an actual number attached before anyone can say how much faster the Santa Cruz Mountains section is moving. When that number arrives, it will do real work. It feeds directly into the National Seismic Hazard Model, which feeds into building codes, insurance rates, and retrofit priorities across the Bay Area. Until then, treat the specific figures floating around social media as fiction. The second thing to watch is whether other groups reproduce the constant rate result on other segments. One field site is one field site. If cosmogenic dating on several stretches of the fault shows the same lack of tapering, the hazard model gets rewritten. If it does not, this stays an interesting local finding. The third thing is the ordinary background. The Coso swarm was still producing small events yesterday morning, in the range below magnitude 1. The creeping section between San Juan Bautista and Parkfield produced 6 small earthquakes in 26 hours, which is exactly what a fault that slides continuously instead of locking is supposed to do. None of that is a precursor to anything. It is the noise floor of a plate boundary doing its job. And here is the honest version of what warning exists. There is no earthquake prediction to suppress, because there is no earthquake prediction. Shake alert is not a forecast. It is a race. Electromagnetic signals traveling at the speed of light against seismic waves traveling at a few kilometers per second. And it buys you seconds to tens of seconds after the rupture has already started. When a magnitude 3.8 struck the East Bay on the 13th of this month, Shake alert activated within 4 seconds and set no public phone alerts because the event sat below the threshold. The system worked exactly as designed and almost nobody knew it had run. Which leaves the one lever that actually exists, and Bliznyuk named it herself. Having an earthquake preparedness kit to prepare us for a potential disaster when an earthquake occurs will really help us deal with the trauma of having an earthquake. Water, a plan, a bolted water heater, a phone charger, and knowing where your gas shutoff is. That is not a dramatic ending. It is just the only part of this you control. The fault will keep moving at the rate it has held for 10,000 years, whether anyone publishes a number for it or not. We will be tracking the peer review, and we will tell you the moment there's a figure worth quoting.